Okay. All right. So I'm going to start the first set of core material. Like I said, I will post these notes and I'll post the corresponding video that goes with it. All right. All right. So what are we doing? All right. A couple of things in terms of the schedule. So basically, homework 1, 2, and 3, you can see the due dates there. Basically consecutive Fridays. And then exam 1, we'll formalize that, but I think probably September 12th. All right, is the first one there. So today we're going to talk about sine waves and we're going to talk about MATLAB. Now you guys should know what a sine function is. All right, I think you should at least. We're going to go over that because a sine wave is a little bit of a different thing than just the regular old sine function. All right. All right. So in terms of material in the book, I do want to give you a little bit of a guide on that. In the first unit of the class, the first unit basically up to the first exam, this is the core material that'll be there. All right. In addition to any kind of prerequisite stuff like calculus, right? On the first exam, I might expect you to do like some integrals or something like that. All right. But basically, when I look at this, chapter 3 goes over MATLAB stuff in the book. All right. I will refer to it. It's got good examples. You may want to look at it. And then in chapter 4, we're going to do a lot of stuff on complex numbers. So imaginary numbers. You saw that probably in high school. You don't see that typically in calc. But you've seen that before, and we'll go over that. Those are the sections that we'll talk about. All right. Which I'll usually mention this at the beginning of every class. All right. So today, sine waves, introduction to MATLAB, and then we're going to talk a little bit about how to plot in MATLAB. So when I say plot, basically I mean to draw graphs. You're probably used to your TI calculator that you tell it to graph something and it kind of figures out the details of how to graph it. All right. With MATLAB, you do have to figure out it's a lot more powerful, which means usually when it's more powerful, it means more thinking on your part to make it work right. All right. So there's some things that you got to do to figure out how to draw stuff. Okay. So we'll make some important points about that as we go through. All right. So sine waves and problems in ECE. So I took two sort of examples here. All right. What's this stuff on the left? Radio signals. All right. So it has a signal and a carrier. All right. So any idea what you would mean by a carrier? Nobody listens to the radio anymore, so it probably doesn't mean anything to you. If I'm listening to, I don't know, give me a radio station. 98.9. 98.9. All right. So I'm going to listen to 98.9. What does that mean, 98.9? Frequency of what? Frequency of the carrier. All right. So basically what it is that's an FM signal. If I had 98.9 megahertz, all right, that means that the frequency is that thing has 98.9 million periods every second. All right. And the carrier waveform does, and it's frequency modulated, meaning that its frequency is changing. So we're going to talk about the meaning of frequency and periods and stuff like that later. But basically, FM is pretty common for a lot of communications, although cell phones typically use AM, which is amplitude modulation. So the word modulate basically means to sort of vary. So what do you think, if I look at the AM waveforms, maybe a little bit more obvious there. What do you think's going on with the AM? How did the signal and the carrier combine to create that third waveform?
You had the signal and the carrier?
Multiplied them.
Oh, yeah.
All right. So I multiplied the signal by the carrier. Now, what's the signal? The signal is the voice signal, right? So if you're on an FM radio station, listen to 98.9, what do? They basically use the voice to change the frequency of that carrier waveform. So in other words, you're encoding the signal, right, the information that you want to send into this carrier waveform. Because I can't send my voice at low frequencies. I can't send it through the air many, many miles, but I can send a high frequency signal through the air many, many miles. Okay. Much more easily. You can do low frequency signals, but it's hard for reasons that have to do with antenna sizes. Okay. All right, we talk more about that, but so sine waves are important. When I say sine waves, what I'm talking about is that there is a time dependence typically to these things. All right, so we're worried about the time. The x-axis typically is a time axis. Almost all of the problems that we deal with in ECE stuff are y, or the x-axis is t. All right, time. Okay. What's the stuff over in the other picture? Any idea what that? So what's this thing here? Anybody seen an image like that before? Yeah, it's what I call a one-line diagram if I'm talking about power. All right. So what I have here is basically two generators. Those are the sources. And those two generators are at different ends of a transmission line. All right. So one of them could be in North Carolina, one of them could be in Tennessee. Those are two generators that are distant from each other, connected through a transmission line. And in the power system, what we talk about, so in the power system, what's the frequency that's used in the US? 60 hertz, right? So that means there's 60 cycles, 60 periods every second. If I was pretty much anywhere else in the world, it's usually 50 hertz, all right? But what I'm looking at here is potentially maybe the frequency could be different in different parts of the system, all right? And so people have tools, the things that I'm showing here, these things are called phasor measurement units. So what they do is they actually measure the phase throughout the system. And power system engineers can look at that to figure out if the frequency is fluctuating and potentially whether or not there's going to be a major fault in the system or whether or not some solar provider out there has got a crappy set of electronics that he's hooked up to the grid, something like that, right? So the notion of how we can analyze and understand sine waves is really important to be able to figure out any of these sorts of problems, right? If I'm talking about audio problems, so that signal up there is an audio signal. What kind of frequencies are audio? What's the frequency range for the audio waves? You guys know? About 20 hertz to 20 kilohertz is about the range. Which side is the bass?
Lower.
The lower side. All right, so you can feel those low frequencies, right? Higher frequencies you don't necessarily feel as much, but we'll talk about that kind of stuff a little bit. So in audio, we're thinking about music problems. We're thinking about audios or sine waves. Okay, so by definition, and this is something that is going to bother you. By definition, the angle of a sine function is in radians. All right. Now, radians basically go from 0 to 2 pi. If I go from 0 to 2 pi, how many degrees do I go through? 0 to 360. All right. Why do you not like that? Because in your calculator, you guys are used to going from degree mode to radian mode. MATLAB doesn't have a degree mode or a radian mode. All right, MATLAB has MATLAB mode, all right, which is basically everything. It is God's honest math truth, right? Which is that the definition of the sine function is defined to be in radians. So if I put in MATLAB, what's the sine of 360 degrees? Right? If I do sine 360, we'll talk about MATLAB functions. MATLAB will not say that it's 0. I don't know what it'll say. It's going to think it's 360 radians. Okay. So how do I convert from radians to degrees? Pi over 180. Yeah. So if I have an angle in degrees, so if I have an angle in degrees, it's a unit conversion, right? So I divide by 180 degrees, pi radians on top, make that multiplication, and then I'm in radians. Okay. If I want to go the other way, I flip the 180, so it's 180 over pi. MATLAB also has functions to do that, but you should know how to do that. Okay. That's just a unit conversion. All right. So the sine function is as a function of angle in radians. And I wrote here xm times sine of theta. All right. So let's just understand this here. So what I did here was I put theta as my x-axis here. All right. What do I call this guy here? X sub m. What's the term for it? Well, yeah. So you guys, so magnitude is a term that's used a lot. Peak is correct because the peak value, what's the peak value of sine? Sine is a function that always goes between what two values? -1 to 1. So xm times 1, xm is going to be the peak value. Sometimes we also call it the magnitude. The proper math term is really the amplitude of the waveform. All right, it's the amplitude of it. So there's 3 parameters that define a sine wave, and we're going to talk about that here in a little bit. When I talk about a wave, what I typically do is I say that my sines are a function of time. So I say that theta is equal to omega times t. All right, so I don't know how it's a new computer. It's a new computer, so I haven't written on it yet. Theta equals omega t. All right, so when I do this, instead of saying I have, sine of theta, very often I write this as sine of omega t, like that. All right, now tell me what should, if sine is defined that its argument is defined to have units of radians, that means theta's in terms of radians. What would be the units on omega there? So if this guy is, you guys should be able to think in terms of radians per second. Radians per second. Now, one thing that's confusing is I keep saying everything's in radians. No real engineer in the world that I've ever met talks in terms of radians. They talk in terms of degrees. All right. I can visualize, degrees pretty easily. If you tell me 50 degrees or 60 degrees, I can think of that pretty well. Anyway, let me pick a random 80 degrees, right? I can think 80 degrees fairly well. I don't know what 80 degrees is in terms of radians, right? I think that's generally true for most people, right? We have a pretty good sense of degrees, but not radians. All right. I put that out there because all these things are defined to be in terms of radians, the frequencies are always going to be in radians per second. Okay. So what I showed here is, so this guy, I showed basically this is sine of theta equal to sine of omega t. There's a couple of ways for me to show this. I've marked out basically this point here is pi over 2. This is pi. This is 3 pi over 2, and this is 2 pi. So it's probably the last time I'm going to speak in terms of radians here. But pi over 2, how many degrees is that? 90. All right, 2 pi is 360, right? Pi is 180. So when I'm looking at this guy here, what's my x-axis here? It's omega t, right? So that basically means theta. What if I had that so that it was in terms of t, not omega t? What would that change about these points? Here, 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 and there. What would it change about those points? The intervals of time, okay? And there we go. I'll skip to this guy right here. So the intervals of time. All right, so what I have here is that same sine function, but this guy now is sine of omega t that I've drawn, and I've drawn it as a function of time. And that's typically how we do it. All right, so we said there's basically in my view, there's 3 key parameters. If I want to draw a sine wave, right, I got sort of a compression thing I can do. I can basically draw any sine wave if I know 3 numbers. Right, what are the 3 numbers that I need to know? I need to know the amplitude, right, which is the peak value. I need to know something about its timing, how often it repeats. And then I maybe need to know something about how much it shifts left or right. Okay, we're talking about that in a second. But I want to talk about it repeating. I probably have it on here, but hopefully you guys know. How long, what's the definition of the time from here to there? So what's the definition of what do we call it to go through one cycle? The period, all right? That period is defined as capital T. So capital T is always a period. Little t for us is always the x-axis, okay? All right, so what I did here is I kind of showed this, so t over 4 is basically where I went through 1/4 of a period. How many degrees is 1/4 of a period? 90. So sometimes it's useful to think in terms of these degrees like this, because you don't know what the frequency of that thing is. This could be a 1 gigahertz signal, or it could be 1 hertz signal, right? You get through 1/4 of a period, right? To get through 90 degrees, it's always 90 degrees, whether this thing is varying 1 billion times a second or 1 time a second. All right. So it's useful sometimes to think of it in terms of those degrees. So to think of the timing, we have basically, so when I say the timing, right, it basically tells me how often this thing repeats. So sine wave is in general what we call a periodic function. All right. What's a periodic function? A function that repeats. All right, and a sine wave is a periodic function, all right, not the other way around. Okay. The definition of a periodic function, does anybody know what it is? I'd say that if I have a function x of t, a periodic function is such that it's equal to what? X of t plus capital T. All right, what does that mean? What did I just write? The definition of a periodic function is that x of little t is equal to x of little t plus capital T. What's that mean? Give me English.
If you have like one period, when you go to add the next period.
If basically if I move a period ahead, it's the same value, right? So the value on the x, sorry, on the y-axis has the same value right now as it will one period later. Okay. All right.
Like the change in face.
No, I like where you're going with that, but not quite. We'll get to that question about phase in a second. All right. Basically, what we're saying is a periodic function repeats, and it should repeat every t. So this is what should also be true about this thing. I could also say this x of t is also equal to what? What other thing could I put there? I could put an infinite number of different things. What also has to be true? The value now has to be equal to the value at now plus capital T. What else does it have to be equal to? How about the value at now plus 2t? That also has to be true, right? Plus 3t minus 17t, right? Always has to repeat. All right, so this is sort of a general statement. Now, oftentimes we don't talk in terms of the period. In other words, the period is the amount of time it takes for it to repeat. Often we talk in terms of the frequency. How fast does it repeat? So what I put here is frequency and period are inverses. Okay, probably know that from physics. And then the angular frequency is 2 pi times the frequency in hertz. So hertz is 1/seconds, right? It's not a hertz, right? A waveform doesn't have a megahertz frequency ever. Hertz is a Hertz, all right? So it's not, sorry, people use it like a plural. It sounds like a wrestling move of some kind to have a megahertz, right? It's hertz, okay? Angular frequency is in radians per second. We use the variable omega, not W, all right? If you tell me it's W, I will always tell you it's omega. Okay, it's not that hard to say it. Those things, we have to know one of these things always to be able to draw this guy, and we always need to know the amplitude. Okay. All right, pretty basic stuff. All right. In general, we don't use the sine function. You see why? Basically, we usually use the cosine function. Okay. Now, why do we use the cosine function? Because any sine wave can be turned into a cosine wave. All right. And it actually gives us kind of a compact way to deal with things. So a lot of you are probably taking 2112 right now, and you're going to use a concept there called phasors. And that phasor basically makes it so that you don't ever really need to use differential equations, all right, which is fun. And so we use it a lot. We use this idea of a phasor a lot. All right, so I want to look at this guy and see if we can figure out some things about it, right? So I said there's 3 key parameters to this thing, right? X sub m, the amplitude, omega, which is related to F, which is related to T, which is tells me how fast it varies. And then I have this guy phi. Use the word phase. Phi is what I call the phase shift of this thing. All right. And what it tells me is how far the cosine is offset at t equal to 0. All right. So tell me, if I had cosine of omega t, and I wanted to draw that guy over a period. All right. I want to show x of t, and x of t is a cosine. It's cosine of omega t. What does that look like if I wanted to draw that from 0 to capital T?
Starts at highest.
Yep. Starts its peak and ends at its peak. All right. And I never draw these trig things very nicely, but you get the idea, right? That's what cosine looks like. What if I wanted to turn that into sine? In other words, I wanted to take this waveform and move it to turn it into sine. let's see, I would need to shift 90 degrees. Which direction would I need to shift it to get cosine? Which way? I would need to pull it to the right, right? Because what's sine always start at? 0, right? So I'm starting at my peak. I want to start at 0. So I need to move it 90 degrees. So I want to move to the right. What kind of shift do I put in there? I want to move to the right 90 degrees. So do I subtract 90 or add 90 here? Subtract it. Subtraction will move it to the right. All right, now you can also look up trig identities online and find all that stuff. All right, but sine of omega t is cosine shifted to the right by 90 degrees. All right, you'll probably want that somewhere in the homework. And you'll want that many times, probably with Yahoo or whoever's teaching 2112. Okay. All right. So what I want to do is I want to look at this waveform here. Yeah, I don't actually, I want to look at it on this page here. I want to figure out from you guys, I want to figure out what is the amplitude and what's the period of this thing. All right. So help me out. Look at this picture here. So this guy is, in general, that whatever I drew here is, this guy is xm cosine omega t plus phi. So xm, omega, and phi all have some number. So I want you to help me out. What is x of m? 10. How do you know that? The peak value, right? The peak value is always the amplitude, right? So clearly it's 10. All right. How do I get the frequency omega? In this picture, how would you get the frequency omega?
Frequency is 1 over period, so this.
Well, so frequency, yeah, so omega is 2 pi f. And how's f relate to period? 1 over the period. All right, so you can go back and look at the notes later to get that summary, but that's basically the relationship, right? So how do I get the period?
Matter for the period, it starts at a certain point and then it returns to a certain point.
Yep, that's right.
But it doesn't matter which point you choose.
As long as I go 1 period ahead, it should have the same value it does now, right? So where would you look to figure out, how would you figure out the period if I gave you this as a homework problem? I'm pretty sure yeah. I would look at peak to peak. You could look at 0 cross to 0 cross, or bottom peak to bottom peak, or anywhere from anywhere, right? As long as it's the same spot. So I did peak to peak. This is something I'll show you later, but in MATLAB, I have these things called data tips, right? So I can basically find a point on the waveform. I have a video that shows you how to get those data points, but I can see it's repeating here. So the value is 10 and 10, right? Looking at the picture, I mean, I can actually kind of tell. So 0.086 to 0.1875, it's not perfect at telling you exactly the point, but how much time looks like it elapses between that, the peak over here and the peak here? Basically 0.1 seconds, right? Yeah, 0.1 seconds. So 0.1 seconds. Yeah. All right, so what's that make the frequency? F. 10. 10 what? Hertz. Yeah. 10 Hz. Okay. And then what would omega be? I don't know. It'd be 2 pi 10. That's how you always hear 20 pi. All right. I don't care what it is. All right. You never really care what the radian per second frequency is. All right. And xm is 10. All right. So apparently what I have here is x of t is equal to 10 cosine of 2 pi 10t. And I got this little pesky phi here. So phi I said was the phase shift at t equal to 0. All right. So what is the phase shift at t equal to 0? Does that look like, here's 0. Is that cosine exactly, or is cosine shifted here? It's shifted. All right. Which way was it shifted? Where did the peak go? Did it go left or right? It looks like it went to the left, although technically it could have gone either way because it just keeps repeating. I can just pull it along, right? But it looks like the peak must have been a little bit earlier. right? How would you find phi? How would you find this unknown value if I gave you this problem? I said, okay, here's a picture. How would I find phi? Any ideas?
Zero.
Set t equal to 0 is well, you could set the equation equal to 0, right? That would work. So in other words, I could say at what value of, I'd have to, if I knew the value of t at which x of t was 0, that would work. What I'm going to do is I'm going to say, well, at t equal to 0, what's the value of x of t? Okay, so what I would say is at t equal to 0, x of t is equal to something. And if I go to the graph, it says it's equal to 7.071. All right. So at that point in time, it's equal to 7.071. And that's equal to cosine of 0t plus phi. No, not 0t plus phi. What am I doing? Cosine of omega times 0 plus phi. Phi of omega times 0, what's that equal to? 0, right? So this is cosine of phi. If I solve for that, what am I going to get? Everybody know? And sorry, the one thing I left out. Sorry. X of t is 10 cosine whatever. So I should have done that this is equal to 10 times cosine of 0 plus phi. Or 10 cosine phi. If I did the math on this, you would see that this guy is equal to 45 degrees. All right. So in other words, this guy actually is x of t equal to 10 cosine 2 pi 10t plus 45 degrees. The plus means that the peak was shifted to the left. All right. Now, what I could also have said, you can think about this later, that it was 10 cosine 2 pi 10t minus, what, 315 degrees? Right? That would have worked too. All right, you can think about that later. We don't typically do that. All right. We typically keep those shifts between plus 180 and minus 180. All right. I don't want to burn your brain with that. It's a pretty simple concept. All right. I think in general, you'll see some of this on the next homework. There's one problem like this on this homework too. Okay. Sine waves are not the most exciting thing in the world, but they're incredibly useful. All right, because not just do all of our sort of application problems deal with sine waves, but the other thing is any periodic waveform is a sum of sine waves. All right, it's possible you saw that in your math classes. All right, if not, we're definitely going to see that. That concept is something called a Fourier series. And that's really useful for us to analyze all sorts of problems. Okay. Because oftentimes, like in the power grid, for instance, we have 60 hertz waveforms, but nowadays when I hook up a solar panel to the grid, and that's basically the biggest thing that's hooked up to the grid these days is solar panels, those don't work with sine waves. They actually put out square waves. But somehow the square waves have to become sine waves. And so that's the analytical tools that we'll need to discover through this class, is how to figure out that kind of stuff. All right. Questions about sine waves? All right. Again, not the most exciting stuff in the world. All right. Now, how did I make the graph that I did there? All right. I'm going to talk about this in some more detail, but if I want to understand how to make graphs, section 3.2 in the book has a whole thing on how to make graphs. You can also go online and find it. All right. I'm going to leave this example here. I'm not going to, so oftentimes I'll have example code like this that you can use. This is MATLAB code here. All right. I'm going to look at MATLAB code here and a little bit more in depth here in a second, but I just want to point out a couple of things. So this was me making X. Okay. Again, I'm going to talk about the details of vectors and things like that here in a second, which is what this is basically an array or a vector. We're going to talk about that in a second. But if you look at what I did 10 times cosine this whole thing. Now, MATLAB recognizes pi as the Greek pi, right? What did I do here, right? So I did plus pi over 4. I said it was 45 degrees, didn't Why did I write plus pi over 4? Because MATLAB always assumes all the trig functions are in radians. Okay. And so I did this guy in radians. Okay. Now, oftentimes what you'll see me do is I'll write 45 times. How do I get, so if I have 45 degrees, how do I get the radians? What do I multiply by? Pi over 180. Normally you'll see me do pi over 180. Back when I was in school, we still used to remember those things. What's 45 degrees? I don't know, maybe you guys remember it. Right? Pi over 3, pi over 4, pi over 6. The important ones. All right, so I just happen to remember 45 degrees is pi over 4. Okay. Now, I want to look at this a little bit more. This is how I drew that graph, but I want to look at this in some detail. All right. Now, I put this in here. If I go to the MATLAB documentation, I will see there sin is the sign of the argument passed to it. So sin of x is the sign of x, where the argument, the number fed to it, is in radians. All trig functions are that way. Now, where did this come from? If I want to get help on any MATLAB function, I can type, like in this case, if I type at the prompt in MATLAB help sine, I can do that. I can also go to Google and type MATLAB sine, and that's actually how I got this page right here. All right. Now, MATLAB has many functions, and it probably has as many functions as there are grains of sand at the beach, right? I will see you guys, particularly as you get into the projects, you'll start using all kinds of crazy ass functions from MATLAB. All right. If you find yourself using a crazy ass function that I've never talked about, you're not doing the right thing. All right. I will basically use whatever I use here, you should be able to use in your homework. All right. I'll see all kinds of crazy stuff appear that I've never seen before in my life. And generally speaking, it's just, what am I asking you to do? I'm asking you to make arrays. I'm asking you to do for loops and while loops and do loops and stuff like that. I'm not asking you to do anything overly fancy, right? There are many, many fancy things MATLAB can do, all right? You're not doing them. If you find yourself Googling looking for a function, you're doing the wrong thing, all right? And you don't know what this means yet, but the day will come when you do, okay? All right, so trust me, you'll remember it when you do. All right. So a couple of things, like I said, all MATLAB functions, trig functions are defined in radians. Part of the reason why I make this point is exponential, e to the whatever, is a trig function. All right, we're going to explore why that is next week. All right, but the exponential function is also a trig function. All right, so you remember that. What I put here is basically 3 ways, or 2 ways, I guess, that I could go from degrees to radians. So MATLAB, sometimes, like I say, you can always, I'll see people do this. They'll spend an hour trying to find the function to go from degrees to radian, right? When you know that I just need to multiply by pi over 180, right? But there is a function, deg to rad. There is a function called rad to deg. What do you think rad to deg does? It takes the argument, goes from radians to degrees, vice versa, right? There's a function for everything, right? And so anything you can think of, there is something that can do it. All right. You don't need to be thinking too hard about finding them. Typically, it's pretty easy just to do in your head. Okay. All right. So MATLAB. All right, let's talk about it a little bit. So today, for the rest of today, and for the end of time, we're going to talk about MATLAB and everything that we do. Okay. All right. You guys know C? That's what they're teaching you in 21, whatever. Or is it Python? C++. All right, C++ and C are the same thing, sort of. All right, as far as I'm concerned. So people will say, I know C, I don't know MATLAB. If you know one, you know them all, and is my basic opinion. In other words, they all do the same thing. They all have variables and they all have that. All right. MATLAB versus C. MATLAB is an interpreted language. What does that mean? I guess I wrote it there.
And so basically run through and act upon.
Yeah, commands are run through an act upon in real time. I don't need to put it through a compiler, generate some object code, and then run that. Okay. I guess I wrote that there. It runs it in real time. The downside, the nice thing about this is I don't need to compile it and see what happens. The bad side of it is bad things can easily happen. I'll give you an example of bad things. When we have interpreted languages, we write scripts, is what we call them. Meaning a script is basically just a series of commands. And so I shouldn't be moving around, but so when you get MATLAB, I like my MATLAB to look like it did in 1997. All right, which was one of the first time I used it. Right. So I make it look like it used to. You'll see it. This is a script that I'm showing right here. MATLAB opens up, and I don't know, there's like 4 or 5 windows within it. All right. I just make it look, like I said, like it looked like in 1997. So what I do is I leave it to just be the command prompt. So at the command prompt, I can do whatever I want. Like if I want to say, what's 2 + 2? It'll say 4. All right. I can run any command. So if I wanted to run that rad deg to rad, let me do it this way, because rad to deg. So what's rad to deg going to do? It's going to give me something in degrees. So I'm going to put pi over 4, and it's going to say 45. Right. So it's, and if I wanted to run multiple commands, what do I do? If I wanted to run another command, put a semicolon. And then I can say, and x equals 2 + 2. And so it did 2 things. When I put that semicolon in, though, I didn't see the 45 here. What? No. Semicolon hides the output. If I don't put a semicolon in, it's going to output it to the screen. Okay. And so that's an important point. All right. You don't need the semicolon ever, but you may want it if you're going to try to output like 20,000 points to the screen. Right. Because it may start writing 20,000 things out. That can slow things down. All right. That's an example of bad things happening. Right. That's not too bad of a thing, but there are some really bad things that can happen. The semicolon basically means that it doesn't output to the screen. All right. One thing I always say, MATLAB is a heck of a lot easier than C. All right. MATLAB doesn't have pointers or any of that kind of stuff that you had to deal with in C and C++. Hope you guys know what pointers are, right? If you took C++. All right. So you don't have to deal with any of that garbage. All right. The example I give is like, what's MATLAB versus C? If I told you to go build a house, MATLAB would be like going to Home Depot to get the stuff. C is like going to the woods with a hatchet. Okay. There's a difference. And I would prefer to go to Home Depot rather than chop down the trees. All right, and plane the wood and all that kind of stuff. C is a low-level language. It's meant to be used at low level, give you a crap ton of flexibility in terms of what you can do. All right, MATLAB, like Python, if you know Python and MATLAB are very similar to each other. Python and MATLAB are both interpreted languages. They have a lot of stuff already defined, and I don't need to worry about memory or any of that kind of stuff. It takes care of that for itself. If you're a real computer nerd, it's written in Java, all right? Although it's meant to look like Python these days. Okay. Anyhow. Now, the other thing is I typically write everything in scripts. Nowadays, people use these live scripts a lot, all right? I don't know a whole lot about them. My recommendation to you is you want to start writing, you go and create a new script. All right. And so I wrote a couple of scripts here. All right. So that we can look at them. All right. All right. So we're going to talk about that stuff here in a second. All right. Some basics. All right. Because MATLAB is an interpreted language, everything that you've done in the past is still defined when you go to run the program again. All right. So at the beginning of your programs, what happens? It remembers. So if let's say I wrote, so just maybe one thing I should talk about real quick. So this script that I have right here, how can I run this? There's 2 ways that I'll do it. In class, typically what you'll see is I'll do this. I'll highlight it, or I highlight a section of it, and then I basically go evaluate selection. All right, and then it'll do it. So it's gonna make a graph for me there. All right, so it made a graph. Cool. All right. The other thing I can do if I want to is I can do run. I think run then asks me to save it. I think the live script, the difference of the live script, it doesn't actually save it necessarily. It just runs that set of commands. All right. For a lot of the early stage homework, you guys can do it all in that browser window in Canvas. But I would recommend that you get yourself familiar with the standalone application MATLAB where you'll have scripts and all that stuff. Okay. All right. At the beginning of your code, you want to put a clear all, right? So if you look at the script that I was showing right there. Oops, that's not the script. That's the command window. I have clear all. What do you think clear all does? Resets all the variables, because if you don't do that, and you called a variable by accident that you've already defined, it may do something totally wacky on you. All right. So that's important to remember. All right. So clear all. And I make this point, code is always correct. Your code is always correct. All right. It always does exactly what you tell it to do. All right. You might be wrong. All right. But your code is. All right. And I make that important point because, you know, if you're thinking about a lot of you guys, computer engineers, you will design what's called firmware, right? What's firmware? You know what firmware is? Probably heard the term.
Low-level programs that run directly on hardware.
Low-level programs that run directly on hardware. So oftentimes, like, let's say, you know, I had a company where we were making inverters, which are the devices that go from solar panels onto the grid, right? And so our firmware engineers basically just sat down, wrote the code, and just uploaded it. And then all of a sudden, we'd hook it up and I would blow up our hardware, right? Their logic was flawed, but their code worked. It did exactly what it was supposed to do. All right. So this is an important point. You want to think before you execute your code. All right. So for instance, that clear all, if I didn't put the clear all in there and I had variables defined, MATLAB's just going to run with it. You would rather MATLAB give you an error that says that variable is not defined, right? Where will this come up? I'll give you some examples of this later. But sometimes I may think that I'm plotting like a nice little simple sine wave. But in reality, I've somehow created a vector that I'm trying to plot that is like, you know, 1,000 by 1,000 by 1,000 by 1,000 size. And it's just, it becomes an insane sort of thing. We'll look at an example of that probably next time. All right. Think before you run your code. Think about whether your variables exist. Do clear alls and stuff like that. One exception, and I make this note, and I'll send an announcement about this. When you go into that browser window that I was showing where you submit your homework, it automatically clears the variables. And the clear all at the beginning of the code confuses it, and it'll give you an error. All right. When you write your scripts, you put the clear all. When you do it in the MATLAB window, you don't do it. If you look in the window, I give you basically all the variables that you need, all right, in the homework submission. You'll see that when you look over that video. Okay. The semicolon, basically what we already said. If I have it, no output's displayed. If I don't, the output's displayed. If it's a big thing I'm looking at, in other words, there's a lot of entries in an array, it'll look enormous. All right, and it may take a long time to print everything. All right. All right, so a couple of things in the time we've got left here. Linear algebra. Everybody's taken, who has taken linear algebra? Sure. All right, let me do the inverse. Who has not taken it? It's okay if you haven't. Nobody has not taken it. That's good. It's supposed to be, but that doesn't always mean things work out. Good. So what's a matrix? You've taken linear algebra. You guys are experts on matrices. So MATLAB, by the way, stands for Matrix Laboratory. Right? That is what it used to stand for. Now it's just MATLAB, I guess. But what is a matrix? Well, all right. So I mean, if you had to explain to someone who had no idea what it is, so it's a way to put a system of equations into, I don't know, a matrix is basically an array of numbers with rows and columns, right? So if I said I had a 2x3 matrix, what is a 2x3 matrix? 2 rows and 3 columns. Okay, 2 rows and 3 columns. All right, so MATLAB's used to dealing with stuff like that. Now in MATLAB, we use 2 types of terms, vectors and matrices. What's a vector? And let me move away, you'll still be able to see it, but what's a vector? A single row or a single column, right? You guys should know that if you've taken linear algebra, right? Sometimes I forget that it's written on there. I like to ask those questions just to, I don't know, just maybe for my own sake to make it feel like you're engaged. So a single column or a single row of entries. So I got two examples here. T1 equals 1, 2, 3, and T2 equals 1, semicolon 2, semicolon 3. All right. Now the other thing that I have there is I have those square brackets. In MATLAB, we use the square brackets to basically say, where does this array begin? Where does this array end? Okay. Now to say that it's a row vector means what? How many rows and how many columns is a row vector? So if I ask you what are the dimensions, that's a matrix, right? T1, 1, 2, 3 is a matrix. What are the dimensions of that guy? It's 1 by 3, right? 1 by 3. 1 row, 3 columns. What about this guy? When I do semicolons, it makes it a column vector. It is 3 by 1. 3 rows, 1 column. What's this guy here? What's that? 2 by 3, 2 rows, 2 by 3, 2 rows, 3 columns. So that, might be, if I looked at this, it'd be 1, 2, 3, 4, 5, 6. If you wrote it by hand, you would write it that way, right? In linear algebra, you would have written it that way. All right, to put that into MATLAB, I would typically do it this way. So what do I do? 1, 2, 3. What's the semicolon doing, do you think, here? It's basically a new line command like you would have in C, right? It's basically go to the next line. All right, so it's saying 1, 2, and 3 are on one row. Semicolon means 4, 5, and 6 are on the next row. All right. Now, if I told MATLAB let me just go to MATLAB and try this. If I go to MATLAB and I did, oops. All right. If I said 1, 2, 3, 4, 5, 6, it'll write it that way, right? So, and if I notice if I don't set it equal to anything, it always says ants equals that. So if I wanted to get it back, I can say ants gives me the answer, right? But if I put another thing in there, ants equals whatever the next thing is that I do. All right, ants is always holding the last value. I don't need commas ever. I think I can have them, but I don't need them. And I don't usually use them. I'm pretty sure you can have them. All right, but what happens if I tried to do instead, what's going to happen if I do, so notice too, if I want to go back to a command, if I push up, I can scroll through easily. All right. One of the reasons why I like MATLAB is I can write everything in a script. If I'm doing a homework problem, I can do everything in a script and I can just run it again. If I make a mistake, I just run it again and see what happens, right? When you guys are used to the calculator and you sort of thumb it in and you made a mistake on step 2 of a 20-step thing, you got to run everything again by hand, right? The scripting process allows you to see everything in a much clearer process. All right. It's one of those things that you got to learn by doing it enough, right? One thing that I always point out is I'm putting the up and down arrows to go to my past commands here. All right, so I can go back and forth if I want to. All right, what would happen if I did this? And I hit enter. What do you think is going to happen? It's going to be just unhappy, right? So I get an error. So vertcat, I could look up what vertcat is. You don't even know. It means vertical concatenate, but you don't need to know that. Basically, dimensions of arrays being concatenated are not consistent. In other words, a matrix, well, what's got to be true about every entry of a matrix? It doesn't have to be square, but each row has to have the same number of columns, right? So if I've got 2 rows here, each of the rows has to have the same number of columns. Right, so it doesn't have to be square. For me to solve equations with it, it has to be square, right? But it doesn't need to be square necessarily. Okay. All right. So MATLAB operates in the basis of vectors and matrices. All right. And MATLAB also has what we call functions. So I think we're gonna pick up with this a little bit more next time. I guess I got a couple of minutes. Let's keep going a little bit. So if I've got this guy T1 and T2, I've got a row and a column vector. All right, so MATLAB has all kinds of functions. I will give you a list of probably the most common ones. But sin is what? Sin is sine. All right, so if I gave sine of T1 there, what do you think I would get out if I did sine of T1? So T1 is a row vector, has the numbers 1, 2, and 3. What do you think I would get if I said x1 equals sine of T1? I would get 3 different answers. And what shape would they be? Row vector or column vector, do you think? Be a row vector. If T1 is a row vector, the output's going to be a row vector. And what do you think the entries of that row vector are going to be? Right? If I looked at x1, x1 would contain, what would the first entry of it be? Whatever the sine of 1 is, and then it would be whatever the sine of 2 is, and then whatever the sine of 3 is. Okay. Now, let's say I wanted to find out what the sine of 2 is. I want to figure out this. How would I get that? Yeah, so I would say I want x1 entry number 2, and it would give that to me. All right. Entry number 2 of that array. Now, in C, the index starts at what? 0. In MATLAB and most interpreted languages starts at 1. All right, so that's going to confuse you a little bit, I'm sure, because you're used to thinking of things starting at index of 0, but it starts at index of 1. Okay. Now, what about this guy here? What would I get for this one? Column vector or row vector? Get a column vector for this one. Yeah. So what would x2 be? x2 would be sine of 1, semicolon sine of 2, semicolon sine of 3. All right, like that. All right, so we have more to say about MATLAB we'll pick up with on Thursday.